Okay, so let's proceed with topic 5 on logic gates and Boolean algebra part 2. So we already covered part 1 last time on the basic logic gates and a basic single variable theorem. And now we go into more details on how we can use logic gates to create a more complex network and also a more complex Boolean algebra methods. So these are other topics that we are going to cover for the lecture this week. We're going to look at the multivariable theorems, the commutation, association, distribution, De Morgan's, simplification theorems, uniting, absorption, adsorption, consensus, multiplying. We're going to look into a little bit more detail on the very important De Morgan's theorem for Boolean algebra. Sum of product of sum formal expression, okay, where we get from the truth table and also with the Boolean algebra, and ways to describe digital logic circuits, analysis of logic circuits, what are min terms and max terms, logic simplification using Boolean algebra. Okay, so let's look at the first topic here, this first subtopic on the multivariable theorems. So there are 4 theorems for multivariable, okay, including the important De Morgan's theorem here. So in the first theorem, it's a basic one, quite straightforward, I would say, the multivariable theorems, where A, B, if you have an AND gate, okay, A and B, you can switch the input, okay, the A becomes B and the B becomes A, and you get the same result. So AB equals to BA. Similarly, for an OR gate, A plus B is equals to B plus A. Association, if you have 3 input gates, okay, 3 input AND gate, 3 input OR gate, you can factor them out, okay, you can factor them out into two logic gates. So for example here, if you have AB, you do AB first, okay, and then C is equivalent to having ABC as one big gate. Okay, there is some difference in the physical VLSI circuits, in the physical circuits, but this on the logic side, the left and the right there are equal, and it's called the association theorem. Looking further at the distribution theorem, so in the distribution theorem, this is a factoring or the distribution theorem, where we can factor out or we can expand, okay, factor or expand essentially. So we can factor out or expand AB plus C in bracket is AB plus AC, just like a normal algebra. And here is another important duality here for the OR, where A plus B is in fact equal to A plus B, A plus C. So this is also very useful and very important, and it's not obvious. So the theorem is not so obvious that A plus B is in fact equal to A plus B and with A plus C. And the De Morgan's theorem we look into more detail later on the De Morgan's theorem. So let's look at the example here. Basically, so A, B, I think we've seen this, okay, A, B, B, A, the same. A plus B is the same as A plus B plus A, okay. Furthermore here, we can see I shown the example here, whereby the ABC is equivalent, okay. So these 3 circuits are equivalent. As I mentioned, in the physical side, if you consider the capacitance on the wire, which signal arrive first, okay, so these signals might arrive at a different time, so the performance might be different, okay. So it might be better to use this instead of this, okay. So it's better to use this, for example, if we have a late arriving C, okay. So if you can imagine a late arriving C, okay, a late arriving C will be better here, since there's a gate delay here, okay. We have a gate delay here, and if it late arriving, so as soon as it arrives, it can already straight away compute, okay, as compared to here, if this is late, then the whole thing is late, okay. Looking at the association, okay, so the association is similar, okay. We're looking at the late arriving. If late arriving C, this is good. If a late arriving A, then this circuit is good, okay. And sometimes this circuit is not so optimum, okay, on the physical level, but they are all 3 are in fact equivalent, Okay, let's move on. Okay, now we move on to the simplification theorems. Okay, so simplification theorem, let's have a look. We have 1, 2, 3, 4, 5, 6, okay, including the Morgans down there. So the uniting theorem is if we have AB plus AB bar, then we can simplify it to a simple A. Okay, so if you can imagine, you have two AND gates with a B inverted. At the end of there, you have an OR gate, so that can be simplified to simply an A. Okay, and then for the duality, okay, for the OR, so this is the SOP, okay, the SOP or the sum of products. This is the POS on the duality. So in the product of sums, the product of sums, so A plus B bar is also can be simplified to simply A. Okay, then that's called the uniting theorem. The absorption theorem is saying that A plus AB equals to A. Okay, we'll look into more details later on. And also here, A, if we factor it out, A plus B is or can also be simplified to simply A. Okay, A plus A bar B equals to A plus B. Okay, and then A plus B bar B equals to AB. Okay, so all this we can prove using the singular and the multivariable theorem that we have looked at in the previous topic and also this current topic. So in the consensus theorem, AB plus A bar C, AB plus BC plus A bar C, A plus B, A bar plus C can be expanded to the following. In the multiplying theorem, A plus B, A bar plus C can be simplified to simply AC plus A bar B. Okay, and then AB plus A bar C is A plus C, A bar plus B. Okay, so here I think it's useful if you can look at each one and try to prove it. And notice that here you can have a different variable. So you can have X, Y, Z, P, Q, R, S. But the idea is, you know, if you have this variable in the first one and the second one here is inverted, okay, is the inverse of it. And you have a different variable, different variable here, different variable here. So for example, X plus, XY plus X bar Z. Okay, so this is similar to this. So we can also expand similar to this. Okay, so not necessarily A and B. And finally, the Morgans, we'll look into more details later on. But just as a quick look here on the Morgan's theorem, it's quite simple. It's quite straightforward and very easy to remember. In the Morgan's theorem, basically what happened is, if we have A plus B bar, which is essentially a NOR gate, okay, can be simplified to A bar dot B bar. Okay, can be simplified to an inverter, basically. Okay, you have an inverter A, inverter B, can be simplified to a simple inverter. And this is equivalent to A plus B bar, which is a NOR gate. A NOR gate that looks like this. Okay, this is so these two are equivalent. Okay, so similarly here, okay, A dot B bar. So what you do is you can break up the A here and then put a plus, and then B also break up. Okay, we get the Morgan's theorem. Okay, so the Bogus Theorem is actually explained here, where we simply break up. Okay, we simply break up. So we have A dot B bar. We're going to break it up and we're going to put a plus. Okay, so similarly here, if you have A plus B bar, we're gonna break up and then we have the end there. Okay. Okay, let's look at an example here. So how can we prove that A plus AB equals to A? So there are several ways to prove. We can prove through a truth table and logic gates. You know, here there's an OR gate here. There's an OR gate here. There's an AND gate there. So you can try all the possible values for A and B and prove that it's actually equals to A. Okay. But here what we can do is we can factor out. Okay, we can factor out. So A 1 plus 1 plus B. Okay, A 1 plus B. So here is actually A plus AB. Okay, so what is 1 plus B? What is 1 plus B? So if you have a B here, if you have a 1 here, what is going to be the output? The output is of course going to be 1. Okay, so you have the annulment there, and therefore here is equals to A. So this is how we can prove that one. Prove that A dot A plus B equals to A. So here is also the same, that we can actually expand it. So A A plus AB. Okay, so AA plus AB. And what is AA? So if you have an AND gate with the same input, it's going to be A. Okay, so here it's going to be A plus AB. Okay, so if you remember, if you have AA, here is going to be A. Okay, and what is this? So here is simply going to be A1 plus B is equals to A. Okay, so let's look at the next one here. Let's look at the next one. Prove that A plus okay, here is a bar here on the top. So about this. Okay, so prove that A plus A bar B is equals to A plus B. So how do you prove this? And in this case, we can make the expansion as follows. So this is using so basically we are going to expand. So A plus A bar, A plus B. Okay. Okay, so this one. Okay, so this one is actually A plus A bar and A plus B, as we've seen. And what is A plus A bar? So A plus A bar is in fact equals to 1. Okay, we've seen in the previous topic. A plus A bar equals to 1, and therefore here is A plus B, and that's it. We cannot simplify anymore. Okay, let's look at the next one here. A plus B, A plus C. Okay, so A plus B, A plus C. Okay, we can expand this. Okay, so if we take this, this is going to be AA plus AB. Okay, so AA plus AB plus AC plus BC. Okay, and AA here is equals to A. Okay, so here is A plus AB plus AC plus BC, and here we already checked that A plus AB is equals to A, and therefore here is A plus AC plus BC, and here is also A, same one theorem here, which is A plus BC, and that's it. We can't anymore simplify further. Okay. Okay, so this is a strategy, simplification procedure, or the strategy that we can follow. Okay, so the strategy is convert to SOP, or the sum of products. Okay, if you have a POS, you want to convert to the SOP. Okay, so here you can just simply make the expansion. Number 2, you can check for exact duplicates and drop. Okay, do we have a duplicate here? So it seems to be that this first terms, okay, the first term and the last term, they are the same. Okay, and remember that A plus A is equals to A. Okay, so therefore that's why we remove 1. Now becomes A B bar plus BC. Check for null values and drop. So is there any null values? So here we can expand A bar plus AB. So A bar is actually 0. This is actually 0. Okay, and the answer is just going to be AB. Number 4, see if one of the items is entirely contained in another. If it is, factor it out. Okay, so can we factor out? Okay, so we see AB and AB there. So of course we can factor out. So AB 1 plus C. And what is 1 plus C? So 1 plus C is equals to 1. Okay, so therefore the answer is AB. Now see if two of the terms are different by only a not function. If it is, factor out all the similar terms. Okay, so again we have AB and AB there. So AB C plus C bar. And what is C plus C bar? This is equals to 1. Okay, C plus C bar equals to 1, and therefore our final solution is AB. Okay, so let's look at another example here. Let's look at another example here. So first of all, what is the goal in minimization? Okay, to minimize literals. Okay, so in this case we have 1, 2, 3, 4, 5. Okay, so here we have 5 literals. Okay, can we minimize the number of literals? Okay, as much as possible. So let's see how many literals we can get. in this simplification. Okay, so x plus y bar plus z. So what we can do is we can simply expand this. Okay, we can expand this, or if you want to go for a shortcut, is simply going to be x plus y bar. Okay, as we remember, is from the previous theorem that x plus y bar is in fact is x plus y and with x plus y bar, which is this term here. Okay, this is not going to be confusing. Okay, x plus y bar plus z. And what is y bar? So y bar is actually 0, so your final solution is s plus z. Okay, and here you have 2 literals only. Okay, so how many literals we reduce? We have reduced from 5 literals down to 2 literals, and we cannot go any further. So that is a simplified, and f here is the same function. Okay, it's the same, exactly the same function. So let's look at another example here. Okay, this one may be a little bit tricky here. Okay, so AB plus A bar C plus BC. Okay, and in this case, we have the same term here for B and for C, so we can actually do AB plus BC plus A bar C, and then we can factor out our B, A plus C plus A bar C. Okay, and okay, so in this case, by looking at this is already the minimized form, and if you look at the theorems, there is no other way that we can simply we can further simplify. But here we have 1, 2, 3, 4, 5, 6 literals, and in this case we only have 1, 2, 3, 4, 5 literals. So we only managed to remove 1 literal from our Boolean simplification. Okay, so let's look at the form of expression. So in the basic rules, connected gates, so I think we have seen this before in the previous topic. Connected gates from a logic network. Output connected to one or more inputs, input connected to one output, most common is the AND OR network. Two formal expression, the SOP and the POS. Okay, so let's have a look at the how to convert the POS. Okay, so here is a product of sum. Okay, the product of sum, and we want to convert to the SOP form. So what is the method? So the method is we need to expand first, number 1. Okay, so here is AB AC bar, okay, plus BC plus CC bar, and CC bar here is 0, so we have the following: AB plus AC bar plus BC. So here is your SOP equivalent. Okay, with 6 literals, and here you have 4 literals. Okay, how to convert SOP, here is your SOP, to POS, POS form. So what you do is we're going to apply the Morgan's law to get the inverse, and then we have to invert back. Okay, so for example here, f is given by this Boolean expression, this Boolean equation, AB bar plus BC bar, and we are going to put a bar here on the top, therefore the whole thing will bar. Okay, and using the Morgan's theorem, we can split it out. So we're going to split this plus here becomes a dot. Okay, and we can split furthermore. So if we keep doing the split here, it's going to be A bar plus B, and with B bar plus C. Okay, and we split furthermore, and eventually we are going to get the following SOP form. Okay, but here is a SOP, not yet POS. We wanted a POS. So here is, remember, here is actually F bar. So here to get F, okay, it's actually equals to F double bar. So we're going to need to bar this whole thing. So then becomes a double bar. Okay, so let's have a look at the next page here. Okay, so F is equals to okay, something strange. Okay, so we are taking this, so we are taking this. Okay, we are taking this, and I'm going to bar it, which is in fact here. Okay, so F is in fact equals to F double bar. Okay, F double bar. So here is actually your F. So your F here just now is A bar, B bar plus A bar C plus BC. This is your F. And here is your F double bar, which is actually equals to F. Okay, so if you double bar that, then you are going to get this plus here going to be a dot, this plus here going to be a dot, and it's going to be separate out. And then we can also separate this out. So here is A double bar, okay, this N here is a plus, B double bar, A double bar, C bar, B bar, C bar. Okay, this dot here becomes a plus, and here is your POS equivalent for F. So this is your F, okay, which is equal to F double bar. Okay, so let's look at the logic network now. Let's look at the logic network. Okay, so let's proceed. Rules to build an AND/OR network. This is the most common. Okay, an AND/OR logic network. So each AND operation requires a one AND gate. Each OR requires an OR gate. Each complemented requires a NOT gate. See the example here. So here is called the AND/OR network. Okay, with the inverter. So you have the inverter here in the front because you require a B bar, and then you have the AND and you have the OR. Okay, so this is called the AND/OR network, and it has three variables, 1, 2, 3. Okay, three variables for product terms, 1, 2, 3, 4 product terms, and 10 literals. Okay, so literal is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And remember, the objective in Boolean simplification is to reduce the number of literals in your Boolean equation. Okay. Let's see a step for analyzing a circuit. So the input to all gates must have a variable name. Okay. So the inputs must have a variable name. So here it should be A bar, B, and then we have A here, C. So each one must have a variable name. So here is A, B, A bar, B, A, C. Write the expression performed by each gate in its output. Do it from left to right. Okay, so this is, we call this here gate 1, gate 2, gate 3, and gate 4. Okay, and from left to right, what is the output of each gate? So here the output is A bar, here the output is A bar, B, and so on. Okay, the output of the last gate is the network equation. Okay, and therefore quite straightforward that the output there is simply F equals to A bar B, which is here, plus AC, which is there. Okay, let's see how we can generate a truth table. Okay, how to generate a truth table for a given Boolean equation as follows. So we know there are the three variable inputs. Okay, there is a three variable network. Therefore, our input here, okay, should be A, B, and C as our input. Okay, and we have to list down all possible input pattern. Okay, so which is 0, 1, 2, 3, all the way until 111, which is 7. And here we are going to the objective is to find the output F for a given ABC. So for example, if I give 0, 1, 1, what should be my F? The answer is 1. And to help generating F, we can also generate what is A bar. So A bar here is just going to be 1, 0, 1, 0, 1, 0, 1, 1, 0, and so on. And then we can generate A bar B. So A bar B is an AND between this and this. So 1 and 0 is 0, 1 and 0 is 0, and so on. Okay, so for example here we can take 0 and 0 is 0. Okay, okay, 1 and 1 is 1. Okay, and then we can also generate AC. So AC is here. So AC, A and C is 0, 1 and 1 is 1. Okay, and finally you can do a plus. Okay, a plus or OR operation between A bar B and AC, you get F. So A plus this one is equals to 1, this one equals to 1, 0, 0 equals to 0, and all the way we can generate our truth table. Okay, let's look at the canonical form. So canonical form is also known as the standard form in writing logic circuits, and is useful for comparing seemingly different functions and is unique for each function. So we have two types of canonical form that we need to know, which is the sum of product and the product of sum, SOP and POS. So from there, we also need to know what is minterm and maxterm. It's related to SOP and POS. So a minterm is an n term where every variable present is either true or in the complemented form. In the max term, the or term with every variable present is either true or complemented form. So let's have a look at the example. Maybe it's more clear what it means to you by the min term and the max term. So let's say we have a 2 input. Okay, here is your 2 input. Okay, what is the min term of the input AB00? Okay, so that's typically the question is what is the min term and what is the max term if the input is 00. So if the input is 00, then our min term is A bar B bar. Okay, and the max term is A plus B. Okay, and for example, if we have 10, okay, so if the input is 10, then our min term is A B bar, because B bar here because it's 0 here. But on the other side, for the max term, if it's 0 is no bar. Only if it's a 1, then it's a bar there. Okay, so in the max term is A bar plus B. Okay, so 1 1 AB, A bar plus B bar, because both are 1. Okay, let's have a look here. So for a 3 variable, we can do the same. Just going to take one example here. I think it's quite straightforward. So for example, if the input, okay, we are talking about the input is 0 1 1, what is the min term representation for input 0 1 1? So it's actually A bar BC, okay, because we have a 0 there, A bar BC. Let's look at the max term. So let's look at the max term. What is the max term for the input 101? It is in fact A bar, because it's a 1. Okay, for the max term, 1 is a bar, 1 here is a bar, and B here, you notice there's no bar. Okay, there's no bar for the B, because B is a 0 for the max term. Okay, and from there we can get the canonical form. So let's look at the canonical SOP form first. So we have our input here and our output. Okay, and what happened is basically you want to get all the ones. Okay, all the one on the output, and from the one we are going to write or generate the min terms. Okay, this is the min terms. Okay, so what is the min term at 0 0 0 is A bar B bar C bar. So we're going to keep this because it's a 1. We're going to keep this one as well, is A bar B C bar, this one. And we're going to keep A, B, C bar, and also A, B, C. Okay, so we are keeping all those in. Okay, so in the end, your F here will be, in fact, A, B bar, C bar, which is this one. And then this one, and this one. Okay, all in the sum. And we can write also as M0 plus M2. Okay, M0 plus M2 plus M6 plus M7. And also we can write similarly, you can put a summation there with the small m, 0 to 6 7. Okay, and that is your min term representation of the output F. Okay, now if given if given a Boolean equation, okay, for example, if you have F equals to AB plus AC bar plus BC, okay, this one, okay, here is convert to convert to SOP. Okay, here is non-canonical, here non-canonical SOP. Okay, here is also sum of products, okay, but it's non-canonical. So how do we convert a non-canonical SOP into a canonical SOP? Okay, so that we can write like this. So what you do is we are going to multiply each of the product terms that is not in canonical by the variable that is not there. Okay, so for example, let's remove this. For example, if I take this, so A, B, and we know there are 3 inputs, A, B, and C. So we are going to multiply with C because C is not there, plus C bar, and remember this is actually equals to 1. Okay, 1 or 0 or 0 or 1 is going to be equals to 1. So it is actually equals to 1, and therefore we can just expand this equals to ABC plus ABC bar, and now this becomes a canonical form, okay, which is this one. So we do the same here. AC bar, B is not there, BC, A plus A bar, Okay, and we can expand all that, simplify if there are similar terms. Okay, we can simplify, and then we can get our equation or representation in the min-term form. Okay, so let's look at the canonical product of sum. So product of sum here, product of sum, we are going to take a 0. Okay, so for all zeros, we are going to take, and if it's a 1, it's going to be a bar. So here is 0, 0, 1, so A plus B plus C bar. We do the same here, and here we have the POS. Okay, we're going to take this down there, and with M3 down there, M4 down here, and M5 down there. Okay. Okay, so in the end, we see that here is actually M1, M3, M4, M5. So we can do M1 dot M3 dot M4 dot M5, and we can put a product here, pi, or the product of M1, 3, 4, and 5. Okay, for the max term representation. Okay, so that's all for the lecture topic this week. So in the next part, we'll discuss some of the exercises for this topic.